In the previous lectures, we discussed about stress strain curve. We discussed about stress strain curve, particularly for mild steel. This curve, right? Whatever you are seeing, right? Frequently in our UG, frequently stress strain curve means we are drawing this curve only. This curve only. This is suitable for mild steel only. Mild steel only, not for all ductile materials. Then we have seen the difference between proposal limit and elastic limit. So in this lecture, we are going to see the stress strain curve for brittle material. Then remaining ductile materials, for example, copper, aluminum, magnesium. First, let me draw the stress strain curve for copper, aluminum, magnesium. Rahul sir, please accept me. I'm trying through mobile also. Solai IITM. Yes. Yes. Yeah, this is the stress strain curve for.
So that one wasn't completed.
Yeah, one second.
Mild steel.
One second. What you are saying?
We spoke about that difference between proportional limit and elastic limit only.
Yes.
So we will continue this.
We did not enter into yield point, right?
Yes.
Yes, I'll discuss it. Let me come here, right? So this is the stress strain curve for copper, aluminum, magnesium. Copper, aluminum, magnesium. So in this curve, we are not able to see the end of the proportional limit. Where is the elastic limit? Where is the yield point and all? Okay, right. Now, come here. Right. So mathematically, we have the formulas up to proposal limit only. Young's modulus, bulk modulus, shear modulus, Poisson's ratio, strain energy are valid up to proposal limit only. Right. But experimentally, we can load up to elastic limit. Right. Reason is, even if you load up to elastic limit practically, while unloading, it will regain the original shape. Right. But the portion between proposal limit and elastic limit is non-linear. Right. Again, we are continuing the loading level. Right. So we are reaching the upper yield point. Right. At the upper yield point, what is happening? If you are unloading, what is happening? If you are unloading, regaining the original shape is possible or not? Regaining original shape is possible or not? While unloading from the yield point? No, not possible. Not possible. So permanent plastic deformation will be formed. Right. So just imagine, in any mechanical or civil engineering machines, right? If any component, mild steel component is deformed permanently, it cannot peacefully run inside the machine or inside the assembly. Right. So it means that whenever the permanent set is initiated, permanent plastic deformation is initiated, that point is assumed as failure point. That point is assumed as failure point. Okay. So no need to go up to ultimate point or breaking point. Right. So mild steel will fail in the yield point itself. Reason? Permanent plastic deformation is initiated. Once the plastic deformation is initiated, it cannot run peacefully inside the assembly. Right. So upper yield point is called as failure point. Failure point. So till the yield point, we are calling the stress as sigma yt. Right. While reaching this point, stress is called as sigma yt. It means tensile yield stress. When the failure occurs, stress is renamed into strength. Stress is renamed into strength. SYT. SYT. Okay. Right. So that is a specialty of upper yield point or first yield point. So upper yield point is the failure point. In that point, we are finding the strength value. Strength value. Okay. Right. So stress at yield point is equal to strength. That's all. Okay. Right. Then only mechanical students see this portion is useful for metal forming process only. Metal forming process only. Okay. Right. For example, during the metal forging. Right. During the metal forging, wire drawing, right? We are using the behavior of this portion, right? But during the application, field application, we are working in this portion only. Okay, we are playing in this portion only. Okay, right. So in the center metal point of view, we have to study the information up to this portion only in detail. Right. So the maximum stress level, loading level is ultimate point. So after that, necking is started. Necking. After the ultimate point, necking is started. Necking. Right. So this portion, right? This portion is used for metal forming process. Right. It is called as flow curve. Right. The last point, breaking point. In this point, the test specimen is broken into two pieces. Okay, so that is a specialty of proportional limit, elastic limit, upper yield point, lower yield point, ultimate point, breaking point. Right. Now, sir, in that mild steel, we are able to find the strength value, sir, easily. From the upper yield point, we are able to easily identify the value of strength, SYT, sir. Here, how to identify? Because it is a smooth curve from the starting onwards. Right. So how to identify? See how to draw. Watch closely. I have to draw the line tangent to the curve. Line tangent to the curve passing through origin. Line tangent to the curve passing through origin. Right. So this is a line. This line is tangent to the stress strain curve. In the same time, the line is passing through the origin. Right. Next, I'm going to draw the another parallel line. Another parallel line. That line should pass through. That line should pass through the strain of 0.2 percentage. Strain of 0.2 percentage. This point is strain equal to 0.2 percentage. This is equal to 0.002. Okay. Right. Now the second parallel line, right? That is cutting the stress strain curve at a particular point. In this point. This point is called as offset yield strength. Offset yield strength. Okay, right. So this number is important, 0.2%, right? So the strength name is offset yield strength, right? So it is a procedure followed throughout the world, right? Next, we are going to draw the stress strain curve for brittle material. Brittle material. Right. This is the stress strain curve for all brittle material. For all brittle materials. Can you give me the example? Can you give me the example for brittle material? Engineering example. Your answer should be related to your department and applications. Brittle material, cast iron, glass, then FRP composites, ceramics, right? So these are the examples for brittle material. Okay, right? Direct straight line. Right? The last point, right, is nothing but SUT. SUT. Ultimate tensile strength. Ultimate tensile strength. Okay, right. So next we are going to draw the stress strain curve for rubber. Right. See, this is forward curve, right? While loading, we are getting this kind of stress strain curve. Right? While unloading, right? This is the curve. Unloading. Loading curve. Right? So this is for rubber. So they will give 4 type of stress strain curves. They will ask which one of the following stress strain, which one of the following is the uh, stress strain curve for rubber. Right? So you have to select appropriately. Now come to stress strain curve of mild steel. Right? Mild steel. So the first point we are going to discuss is strain energy. Strain energy. Right? So what do you mean by strain energy? Or let me write the Hooke's law first. Hooke's law. What is the first word of the Hooke's law? Hooke's law definition. How to start the Hooke's law? Anyone please answer? How to start the Hooke's law?
Within the proportionality limits.
Yes, correct. Within the proportional limit. That is the expected one, right? Within the proportional limit. Within the proportional limit. Stress is directly proportional to strain, right? So sigma is directly proportional to strain. Sigma is equal to Young's modulus into strain. So the proportionality constant is Young's modulus or modulus of elasticity Young's modulus or modulus of elasticity. Okay, so it is a material property. Right. So E is a material property. E is material property. Okay, right. So epsilon is strain. Strain is also material property. Sigma is stress. Stress is geometric property. Geometric property. Okay, right. Then what is the slope of the stress strain curve? What is the slope of the stress strain curve up to proportional limit? Slope of stress strain curve up to proportional limit. Right. Answer please. Slope of the stress strain curve. Young's modulus. Young's modulus. Very good. Young's modulus. Okay, right. Young's modulus. Right. Then already you discussed related to Hooke's law. One more information already we discussed. Young's modulus, bulk modulus, shear modulus, Poisson's ratio, strain energy, Hooke's law. The strain depends upon the modulus of elasticity or Young's modulus. That is why strain is called as material property. There is an interview question I will discuss later related to your doubt. Are valid up to proportional limit. Valid up to proportional limit. Right. Now, resilience or strain energy. Right. See, very important term, strain energy or resilience. Strain energy or resilience. Right. So when we are doing the work or when we are applying the load on the specimen, uniaxial tensile test specimen, it is undergoing del L, right, up to proportional limit. Right. See, it means that this is a specimen, it is applied load. So elongation is del L. Right. Del L. Load is displaced for the distance of del L. Right. What is the product of P into del L? Tell me, what is the product of P into del L? What is the product of P into del L? Force into displacement. Force into displacement. Work done. That's all. Work done. Very simple. Work done. Right. So the work done is nothing but energy. So work done by us. Work done by us. We are applying the load, right? Work done by us on the external surface of the specimen is stored as a energy inside the material. Right. So already you know we are loading up to proposal limit only. It means that the energy is stored inside the material, right? Strain energy that can be recovered while unloading, right? Now we will give the definition. Energy is stored in the material when it is loaded within proportional limit. Within proposal limit. Right. Strain energy is recoverable. Strain energy is recoverable. Recovered while unloading. Right. Suppose, see, you are loading up to here. The energy stored is strain energy. You are loading up to here. Energy stored is strain energy. You are loading up to here. Energy stored is strain energy. Right. Sir, if I load up to proportional limit, that will be the maximum possible strain energy. That's all. That will be the maximum possible strain energy when you are loading up to proposal limit. Right. That is called as proof resilience. Proof resilience. Proof resilience. That is SE max. Maximum strain energy. Right. So what is the definition? Same definition of resilience, only small changes. Up to proposal limit. Up to proposal limit. Okay, right. Now, for comparison purpose, one component may be smaller one, another component may be larger one. So depending upon the amount of material available, the energy stored will vary from component to component. Then how to compare the strain energy level means strain energy per unit volume of material. Strain energy per unit volume of material, right? That parameter is used for comparison purpose. Right? So already you know, right? Theory of failure. We are going to discuss about 5 theories of failure. Out of 5, last 2 theories of failures are based on the strain energy only. Strain energy only. Right? For example, within means if you load up to here, within proposal limit, right? Within proposal limit, right? If you load up to here, it is called as within the proposal limit. Right? It is strain energy. We can load up to proposal limit, maximum of proposal limit. Okay, it means up to. If you load up to proposal limit, the energy stored will be the maximum value. Is it clear? Right.
Excuse me, sir.
Yes.
what happens to strain energy after the proportional limit?
Here, energy will be there. It can be recovered, but we don't have the formula, right? The same mechanism is happening between proportional limit and elastic limit also. Okay, but we don't have the formula. That is why we are not discussing, right?
Okay, so the energy still does exist there.
Yeah. Energy will be there because elastic property is available up to here, right?
Okay.
Right. So the maximum.
Does that mean throughout the whole curve that energy will exist?
That we will discuss next. I will come, right?
Okay.
So right now we are discussing about strain energy only. Strain energy is recoverable. That is important point. Strain energy is related to elasticity. It is related to elasticity. Right? So don't forget, strain energy is related to elastic property. Right? So the maximum possible strain energy is called as proof resilience. It is a new term. Try to remember this name. Right? Then for comparison purpose, we are using the term modulus of resilience. Modulus of resilience. Modulus of resilience. Modulus of resilience. Right? So what do you mean by modulus of resilience? Proof resilience. It means maximum strain energy per unit volume of material. That's all. Proof resilience per unit volume of material. Proof resilience per unit volume of material. Right. It means SE max per volume. Okay. Right. So this is used for comparison purpose. Used for comparison of materials. So example is out of 5 theories of failure, the last 2 theories of failures are based on the strain energy. Right? The fourth one is Beltrami theory. Beltrami. Right? So Beltrami theory of failure, they are using the parameter of total strain energy per unit volume of material. This parameter is used for comparison purpose. Right? So we have to calculate the total strain energy per unit volume of material in our actual component. For example, beam. We have to calculate. In the same time, we have to calculate the total strain energy per unit volume of material in the uniaxial tension test failure point. These two parameters should be compared. Okay, right. So strain energy per unit volume is used for comparison purpose. Another example is von Mises theory. Von Mises. Von Mises theory of failure. In that, shear strain energy per unit volume of material is used for comparison purpose in the theory of failure. Okay. Right. Now, tell me, what is a unit of modulus of resilience? Unit of modulus of resilience. Unit of modulus of resilience. Joules per meter cube. Then for proof resilience, joules. Resilience or strain energy, joules. Okay, strain energy. unit, right? Now we are going to discuss about 3 types of loads. Did we discuss earlier 3 types of loads? No, right? All of you see here. We will complete this, then again we will go back to strain energy topic, right? See, all of you see, we are going to apply 100 Newton force on the component. Okay, right. 100 Newton force on the component. In what way or in what fashion you are going to apply the 100 Newton? That is a matter. For example, first student is applying the force like 0 Newton, 1 Newton, 2, 3, 4, 5, 90, 91, 92, 93, 94, 95, 96, 97, 98, 99, 100. Gradually applied load. Gradually applied load. Right. So we are using this type of loading in our UTM. In our UTM. Gradually applied load. Okay. Right. It is called as gradually applied load. Right. So initially it was 0. Final load is P. Or let us say it is a W. W. Right. Final load is W. Right. What is the average load? P average. What is a P average? Tell me. Average load. Quick. Average load. Average load. W by 2. That's all. W by 2. W by 2. Okay. Right. So it is used in UTM. This method is followed in UTM. This method is followed in UTM. Right. Next. So this is a table. This is a table. We are going to keep 100 Newton weight just on the table directly. Right. So it means we are not applying the load gradually. All the full loads are applied in a fraction of second. Right. Full 100 Newton load is applied in the fraction of second. So what will be the loading curve? This is the loading curve. Okay. Right. Initially it is W. Okay. Now tell me, what is the average load? What is the average load? W. Very good. Very good. So this method is called as suddenly applied load. Suddenly applied load. P sudden is equal to W. Right. Then third case, impact case. Right. Same 100 Newton, right? 100 Newton only. W is equal to 100 Newton only, but it is dropped from a height of H. Okay, right. Now, when we are dropping from a height of H, what is the effect of load? All of you see here, the weight is W, dropping height is H, right? The original material cross section area is A, length is L, Young's modulus is E. Okay, right. Now I'm going to write the impact load details. Impact load Impact load. Right. Impact load is equal to P impact is equal to W into 1 plus 1 plus 2H by del L static. See the multiplication factor. This is the multiplication factor. Okay. So actually you are applying the W only due to the drop, due to the impact, right? This is the multiplication factor. Right? Even though the H dropping height is negligible, very small. How many times the W will be multiplied? Tell me. How many times W will be multiplied even though it is dropped from a negligible distance, very small distance. But you are dropping, right? That is where. Only thing is, even H is small, minimum of how many times W will be multiplied? Answer quick. 2 times, minimum 2 times, right? So the actual impact effect will be minimum 2 times or greater than 2 times. Okay, right. So you have to understand. Sir, what is a del L static, sir? Right. You know, right? Suppose if you are applying the load here, without dropping, right? Static load. What is a del L formula? Del L formula, change in length formula. Or 1 second. See, stress is equal to E into epsilon. P by A is equal to E into del L by original length. So from this, what is del L? Very good. Del L is equal to PL by AE. Very famous formula. Very famous formula. So del L static is equal to PL by AE or WL by AE. Okay, right. So these are the 3 methods are applying the load. Same amount of load, but method of applying the load is different. One is gradually applied load, like our UTM, then suddenly applied load, then impact load. Right. Now come to our stress strain curve. Okay. We are going to calculate the area under the stress strain curve up to proportional limit. Area under the stress strain curve under the stress strain curve up to proportional limit. Right. See the portion. It is in triangular form. Okay. Right. What is the area? What is the area formula? General formula for triangle of BH. Right? Of BH. Right. Area is equal to of of BH is equal to half into stress into strain. Right? Half into stress into strain. BH or HB, anything. Right? Now expand it. Half into P by A into del L by L. Okay. Right. Stress and strains are just expanded. That's it. Now, which type of load is applied in the UTM? Tell me, uniaxial tension test. Which type of load is applied? Quick. Which type of load is applied?
Gradually applied load.
Gradually applied load. What is the effective gradually applied load? Effective load of gradually applied case. Effective load or average load, anything. P by 2. P by 2. Okay. Right. See this group. Effective gradually applied load half into P. Right. So effective load into displacement is what? Tell me.
Work done.
Work done, or strain energy, right? Then in the denominator, cross section area into length of the specimen, volume, right? Now is equal to strain energy. So since we are loading up to proportional limit, we can say it is maximum strain energy per unit volume of material. So what is the name we have given for maximum strain energy per unit volume of material? Modulus of resilience. Modulus of resilience. Modulus of resilience. Okay, right. So this is the answer. Area under the stress strain curve up to proportional limit is equal to modulus of resilience. Okay, right. We can give the another definition for strain energy. Energy stored in the material by virtue of elastic deformation. Energy stored in the material by virtue of elastic deformation. Okay, right. Same meaning. Right. Next, see here, Alap is here. I'm going to draw the modulus of strain energy. This is the modulus of strain energy. Modulus of strain energy. Right. Now, already I told, right? When we are going for metal forming process, for example, metal forging process, in order to make a connecting rod of an IC engine. Right. So, IC engine connecting rod is made by metal forming process, forging process. Right. So, in that case, how much energy we have to apply? That we have to calculate. Now tell me, while making the metal forming, right, the material is loaded up to proportional limit or up to last point, or up to ultimate point. In the metal forming process, see the question is, in the metal forming process up to ultimate point. Right. So during the metal forming process, this portion is used. Right. We should not use this portion because necking is formed. Material starts separating. Right. It means inside crack is formed. So we should not use this portion. Right. So during the metal forming process, we are using this portion of stress strain curve. Right. So we have to know how much energy we have to apply. In order to convert the given billet into connecting rod. Right. So during plastic deformation also we need energy calculation. Right. That is another point. Next, there is a bumper in the car. During the accident, the bumper is fully collapsed. Right. So how much energy is absorbed by the bumper till last point, breaking point? Right. During the accident, we cannot have the control whether it is propulsive limit, elastic limit, ultimate point, breaking point. No chance to control. It will be loaded till the failure, last point. How much energy will be absorbed by the bumper? That we have to calculate. See, in that case also, energy related to plastic deformation should be calculated. Right. So I gave two examples. One is metal forming process, another one is accident case bumpers. Right. Now, area under the full stress strain curve. Is nothing but modulus of toughness. Modulus of toughness. Area under the full stress strain curve is modulus of toughness. Modulus of toughness. Now, tell me the definition for modulus of toughness. Energy absorbed by the material by the material by virtue of plastic deformation. By virtue of plastic deformation. Say example for this case is bumper under accident. Right. Then metal forming process. Right. What is another definition for strain energy? Energy absorbed by the material by virtue of elastic deformation. Both are energy.